Good evening, everyone. Let's wait until 7:05, and then we start. Okay, I think it's time to start. So this is our last lab session, and in this session, we're going to practice how to use recurrent neural network and LSTM to deal with time series or time series data or sequential data. So let's look at the notebook 6A, time series forecasting. So in this notebook, we're going to predict passenger numbers uh, in the future or for the next month. So this is the data set we are working on. So it is a airline passenger data set. So there like 1,000 1,000 rows in the in the data set, and it only has two columns. The first column indicates the month of the record, and the second column would be the passenger numbers in the specific month. And the data all comes in order according to the ascending order of the time. So it so that's why it is time series data. So the data has already been sorted based on the according to the time. So we first read the data set. Again, we use read CSV to read the CSV file, and we can just visualize the first few rows. So here we just visualize the first 10 records. You can see uh, the first column month is just purely year and month, and the second column is the integer number representing the passenger number. And we want to convert because the first column month uh, by nature after read in they are just pure string, and the program doesn't know their ordering. We cannot just compare their values. If we compare them directly, they are compared based on the comparison rule of string instead of treat them as the date time. So the first thing we need to do is to convert this string representation for the year and month into the date time. So we call the toDateTime function of pandas library, and then providing the first column and let the function to determine the datetime format. So we set it to true, and we use this line to convert the string representation into the datetime value for the first column. And then we set the first column month as the index of this tabular data. Before we set the first column as index, it just use some integer values starting from 0 to be treated as the index. But we want to set the first column, the date time of each record as the index, so that later on we plot the data set, it will be more convenient for visualization. So now if we visualize the modified data frame again, we can see now the month has already been treated as daytime values, and the first column month has already has become the index for each row, and the second column passengers remain the same. And then we can plot the data using these curve lines. So what we can observe from the visualization, the first thing is we can see there is a upward trend in the passenger numbers. So the passenger numbers generally increasing with the time. And the second observation would be there are some seasonal patterns. We can observe such kind of repeated going up to the peak, and then the passenger number decrease to a certain trough, and then going down. We can see such kind of repeated pattern frequently, and the interval or the time range for each repeated pattern may be roughly around 1 year. So it kind of yearly repeated pattern. Sorry. And we can also observe that the seasonal fluctuations getting larger over time. So at the early time, we can see the fluctuation or the distance between the peak and the trough is relatively smaller than the later time. So after 1960, we can see or we can observe a large difference between the peak passenger numbers and the trough passenger numbers. And the next thing is we would like to normalize the data. So the machine learning models or the deep learning models um, works well when the numerics are in a controlled or small range. So normally we prefer to scale the data range into the range between 0 and 1. So we um, after normalizing the data, it will make the optimization more stable. So we would use the min-max scaler and specify the range that we want to comprise the data that is between 0 and 1. So we use this min-max scaler to scale all the passenger numbers in the data set. Then, after scaling the data, it's time to split the data into train and testing set. So again, we use the train test split function, providing the entire data set, and we want to preserve 1/3 of the entire data set to be a testing data set. So we have 2/3 of data used for training and 1/3 of data used for testing. And the major difference is here, shuffle equals to false. Recall that previously, when we were working with some tabular data, um, we always shuffle the entire data set and then do the train test set split. But here, when we are dealing with sequential data or time series data, we don't want to shuffle the entire data set because the data comes in order. If we shuffle the data set, their order cannot be preserved. And later on, when we prepare the training samples, the data will not come in order. They are not time series data anymore. They will be treated as just regular um, tabular data. So it will not persist such characteristic anymore. So we want to preserve this useful order information. So we don't shuffle the data during the split stage. So now we have do the like data type conversion, normalizing the data and split the data into train and test set. And now it's time to prepare the training samples and testing training samples and labels, and also the testing samples and their corresponding labels. It is a supervised classification task, right? Not classification, it's supervised regression task. So it comes with true label. We know our expectation on what will be the passenger number in the next month. That is the month we are going to predict. So we prepare the input data and their label through calling this function, create data set. So it accepts two parameters. One is the entire data set, and another parameter is used for specifying the time step. So that means how many previous months are we going to use to predict the next month? Let's say if time is set to 1, that means we will just use the previous 1 month's data to predict the next month. So what if the time is set as 6, that means we will use the last or previous half year's data, passenger numbers, to predict the next month's passenger number. So this time is specifying what are the time steps in previous months that we are going to use. Here we just create two container. These are two lists to store the data for input and data for true label. And it just loops through all the data set, and then it, it extracts the first few months data and then treat the and save it as a variable A and append this variable A to the input data set. So that means we will first extract the first few months passenger numbers and treat it as a kind of list of records, and then append this list of record into the input data list. And then for the label of this uh, corresponding records, we are going, because we are predicting the passenger number in the next month, so we just pass in the index of the following month's passenger and extract the value and append it to the true label list, so that the label and the input records list matching with each other. And then as the return value, we return both the input sample list and the true label list. Now, after calling this function, we will get the data set, the inputs and their labels ready for training and also for testing. Let's see how we get them prepared. So here, in the first example, we simply set time equals to 1. That means we only use the previous 1 month passenger number to predict the next month's passenger number. And we call create dataset. We provide the training dataset and the time step number. And the return will be the training input and the training label. We will do the same thing on the testing dataset. So we just supply a different set to prepare the input and labels. And then we reshape the input data. So why should we reshape it? Because after calling this create dataset on the returned training data should come in size samples and features. So the size of train X should be samples and features. So for the samples, because we preserve 2/3 of data, that should be around, let's say, 666 data samples. And for the features, what are the features? Features are the passenger number for each month. So that means the feature would be just 1. So this would be the prepared data after create function. But what we are expecting for the model input is samples, time steps, and features. So that means we need one more dimension. So we need to reshape this 2-dimensional data into 3-dimensional data. So we need to reshape the provided training input into 3 dimensions. So it specify it should not be the feature. It should be the time steps. This should be the time steps, not the features. The shape of the train X should be the samples by time step as its size. But the model, the RNN model or the LSTM model is expecting the input come in this size, samples by time steps by features. So we need to reshape it into this shape. So the first train X dot shape 0, that would be the samples, and train X dot shape 1, that would be the time step we specify. That should be 1. And the last dimension, that is corresponding to the feature numbers, because we only have one features per month, that is the passenger numbers in that month. So we specify 1 as the third dimension. And we do the same thing for the test input. So we also need to reshape the test input so that it can, during the test stage, we can feed this input data for prediction and evaluation.
Excuse me, doctor, can I ask a question?
Yeah.
Okay. Because from assignment to it assessment one, I got the feedback is that imputation parameters were learned before the train and test split. So in this lab, did the data, the parameters been normalized before the training and test split? I would just a little bit.
Yeah, this is just for demonstration purpose. It is not in practice. We should not do the normalization. Where is it? We should not do the normalization before split. We need to split it first and then do the normalization. And the min-max scalar should only apply it or calculate the transform based on the training set only instead of on the entire data set. So after we call fit transform on the training set, we then need to apply the scalar on the testing set as well. So we need to first do the split and then normalize the data. That's
Mm.
that's a practical what we do in practice. So this notebook is just for demonstration purpose, and this part is not our focus. So just make it simple to write.
Okay, got it. Thank you.
Yeah. So after we prepare the input data in the expected format, that is that will be accepted by the model, we can now build our recurrent neural network model, the RNN model. So again, we use sequential, and we add the simple RNN layer, and we specify the hidden state vector should come in length 4. Always say there are 4 hidden units in this layer. And we need to specify what's the shape of the input. So you have seen that the shape of the input should come. The first dimension is corresponding to the batch number, so it will be ignored in this input shape. And so we need to match this second and third dimension with the input shape. So the first dimension should be time step, and here is specified through the time variable. And the second dimension, that should be corresponding to the feature numbers. And we only have one feature values for each time step. So that is the passenger number in that month. So that should be 1. Therefore, the input shape should be time by 1. And then after setting up the simple RN, recall that there is another parameter called return sequences. So if return sequences is set to true, it will return all the hidden vectors, hidden state vectors. But here, what we care is only the last hidden state vector. So the return sequences parameter should be false. And by default, that parameter is set to false. So we just ignore, we don't need to specify that parameter values explicitly. So we just leave it blank.
That's good. Sorry, quick question here. The problem we are trying to solve is predict the number of passengers in the sequence of coming months.
Yes.
So given that, like since the prediction number we are looking for is the number of passengers, why did we
Yes.
consider the number of passengers as the feature?
Sorry, what's the last question?
Yeah, so why we mentioned that the feature we have is number of passengers, but number of passengers is what we are predicting, right? Not the feature.
Yes, the number of passengers is the data we are using, and it will also be the number we are going to predict.
Isn't the feature is the month?
No, feature is the passenger number. Let me see. Let me find the slides. Can you see the slides?
Yep.
Yes.
Okay. So this is the RNN model, right? So we are not working on the text data, so we don't have this word embedding. So we just need to, so we don't have this stuff. And we are working on the pure numeric values. And so x0, that might be the input vector. So it should have like, it should be a vector of maybe passenger numbers. And this is passenger number for first month, and this is passenger number for second month, and this is passenger number for third month. So we just keep supplying like previous month data, and we don't need this part. We only care about the last hidden state vector. That would be maybe we are predicting the passenger number at month t. And this is what we are doing. So why we treat them as why there is only one. This is the feature. This vector is the feature vector we providing. So in this case, because each month only has one value or only has information about the passenger numbers in that month. But what if the situation changed to, let's say, we are doing the stock price prediction? We may have the, let's say, the first day's open and closing and highest maybe price. This is for the first day. And this is the second day's open, close, highest value, and so on. So in that case, for each time step, we may have multiple features. So we may have one feature representing the opening price, one feature representing the close price, one feature representing the highest price on specific day. So in that case, the feature number is not one. The features number will be like in this case, it will be 3. And the and then the input shape will be like time, and this will be 3. Does it make sense?
It does. Just to make sure I understood it correctly. So the output is also will be three values, right? Whichever the matrix or the vector that it will be, there will be 3 values, like the starting, ending, and the other one.
Uh,
At least the hidden
it
state.
depends. It depends. Let's say for stock price prediction, the input feature numbers is defined by us because we know how many features we're going to supply for each day, right? So this feature, it can be a feature of 3 or a feature vector of 2 elements. It depends on what information we supply. But for the output, here, the shape of hidden state vector is also specified by us. We can use a vector, let's say a vector of 16 or 32 or vector of 8. It doesn't matter. It is just a vector containing some memory information. This memory information is summarize all the information it has been processed by this recurrent neural network or this computation blocks. After we got this hidden state vector, we need to use some dense layer to connect to this hidden state vector and then do the prediction. If we want to predict 4 values, we use 4 neurons in the output layer. If we only need 2 values in the output, we can just keep 2 neurons.
Thank you, Dr. Answer.
Yeah. Okay. Okay. After we set up the RNN layer, it's time to connect this layer output, that is the hidden state vector, with the model output. So we use the fully connected layer or the dense layer to set up this connection. So we add one more dense layer because it is a regression task, and we only interested in the single value, that is the passenger number. So we only care about what's the passenger number in next ones. So it is just one scalar value as the output. So we use a layer of 1 neuron to do this task. So this would be our output layer. And this layer of 1 neuron, the neuron will be holding the predicted passenger number in the next month of the sequence. And then we compile the model, providing the loss function. We use mean square error as the loss function because it is a regression task. So we can simply compare what is the difference between the predicted value and the true passenger number value. So we calculate their square difference and then calculate the mean for the batch. And for the optimizer, we use the ADAM optimizer to fine-tune those parameters in the RNN and also in the fully connection layer. And then if we visualize the summary of this neural network structure, we can see it has only 2 layers. One is the RNN layer, and another one is the dense layer of 1 neuron. So how did we get these parameter numbers? So recall that the parameter numbers of the RNN depends on the shape of the input vector and the shape of the hidden vector. So for the shape of input vector, this is the time step. It doesn't affect the input vector x. So what matters is this one. This one specifies the length of each input feature vector x. So the shape of x should be 1. Recall that the hidden vector is denoted as vector h in the lecture slides. So the shape of h should be 4. This 4 is specifying the length of hidden state vector. So that would be 4. So how to calculate this number? Recall that all these parameters are stored in the weight matrix of this RL layers. And the size of the weight matrix would be 4, that is the shape of H, multiply the shape of H plus the shape of X. So that would be 20. And this 20 is not including the bias parameters. So after we're adding the bias parameters, that would be 24. So the bias parameter numbers are equal to the number of or the shape of hidden vector state, the hidden state vector. So we need to add 4 bias parameters. And for the fully connected layers, the parameter numbers that is straightforward. We have 4, that is the output shape. It is also the length of the hidden state vector. So we need 1 edge. So in total, 4 edge to connect this output neuron with each element in this output hidden state vector. So 4 edge, each edge has 1 weight plus 1 bias parameter. So in total, there will be 5. Okay, let's move on. So now we have built the RNN model, and we can start training. So we call model.fit, providing the training input and the training labels. And we simply just train it for 100 epochs, and each mini batch will be has 1 training sample, and verbal stereo will just print no extra debug information. So after this line, the model will be trained, and we can call predict function to get the prediction out of our trained model. And we can also test the model on the testing input. And here is the important thing, that recall that we already used the min-max scaler to scale the range of the data into the range between 0 and 1. Therefore, the prediction out of the model will be a value between 0 and 1. But we are expecting the model prediction to be a passenger number. And it is not reasonable to just report a floating number between 0 and 1 to be as the passenger number. So we need to convert this small number back to the range that is representing the actual passenger numbers. So we have done this min-max scaler to scale it down. Now it's time to reverse this transformation. So we call the inverse transform. of the same scalar on the prediction result. So this function will convert the value that is between 0 and 1 back to the passenger number range. And we did the same inverse transformation on the training labels because the training label is also scaled down. That is, the training label is also a passenger number, and it was also scaled down by the scaler. So we also need to scale it back. So we did the same thing on the testing input, on the testing data, and this is the prediction on model prediction on the testing data, and this is the conversion of testing labels. We need to convert all these passenger numbers back to the integer range or into the original passenger number range. And now, after we've done this conversion or inverse transform, we can calculate the prediction and true labels difference or the model performance. So we are using the root mean square error. So what is the root mean square error? We know that the mean square error and the root mean square error is just the square root of mean square error. So we just call the mass dot square root on the mean square error between the true label and the model prediction. If we call it on the training data set, then that will be the returned number will be the training performance. If we call it on the testing data, that will be our test performance. And we can also calculate the R2 square on both training and testing set to check the performance of the model. And we can see that the lower the root mean square error must be, the better the performance, right? Because smaller value will indicate a smaller difference between the prediction and the true passenger numbers. And higher value on the R square score will indicate better performance. We can observe that the performance on training data is much better than the performance on testing data. This discrepancy between training and testing may not suggest that it is a overfitting problem. One cause may be because the nature of the data we have. If we later on here. So if we plot the data used in different sets, we can see that the blue curve, that is the original entire data set, and the orange curve would be the data set we use for training, and the green curve would be related to the data set we use for testing. We can see that the early 2/3 of the data are used for training, and the later 1/3 of data are used for testing. And the characteristic of training and testing are quite different. We can observe that the fluctuation or the peak and trough difference in the testing data is much larger than the training data. Maybe because of such difference, the model may have downgraded performance on the testing data set. So we cannot just simply conclude that because it has higher training performance than the testing performance. We simply just conclude that it is an overfitting problem. We'd better not in this case. So there are many other factors that can result in such difference, not only just the overfitting problem. Okay. So we have tried to build a model that only rely on the previous 1 month data to do the prediction. What if we provide more information? What if we look back at the past 6 months data and use this 6 months data to make the prediction? Maybe the performance could be improved. So here, we simply change the value for this time step from 1 to 6, and we will keep all the rest the same, like same model structure, one RNN layer, one dense layer, same hidden state vector length, and same input shape. And for model training, we just use small batch optimization, and all the rest kept the same. And if we observe the performance difference, now the training performance is 21.9. That is that is better than the time step 1 version. But for the testing performance, it has 57.79. That is larger, much larger than the the time step 1 version. So it may suggest that the performance of this 6 time steps version is worse than the 1 time step version. So it is kind of counterintuitive to our understanding. So why, when we provide more information to the model, why the model didn't improve? That may be because that the repeated pattern for this curve, or the seasonal repeating pattern maybe span over 12 months instead of 6 months. And if we do the prediction based on the past 6 months, it may just disguise the model to make even more wrong prediction. That could be one possible cause. So simply providing more information to the model is not guaranteed to improve the model performance. So it's still affected by the nature of data and some internal patterns persist in the entire data set. And what if we change the RNN layer to LSTM layer? So we have seen in the lecture that the LSTM is kind of more complex model, and it can tackle some drawbacks of the recurrent neural network, especially for the gradient vanishing problem. The RNN model is bad at dealing with long memory information, and LSTM can work well on that. So what if we replace the RNN layer with this LSTM layer? So let's first start with the time step 1 version, and we keep everything the same. Same sequential model, same hidden state vector size, same input shape, and the only difference is this layer name. So we are not using RNN, we are using LSTM. So now if we observe the performance, we can see that the training performance is around 22 and testing performance is 49. So if we go back and see, it is quite it is relatively the same level as this RNN version. why? What's the explanation for that? So we know that LSTM is better at dealing with long memory. So it uses the cell state vector to decide what information to be kept and what information to be forgotten. Um, the advantage of LSTM is to dealing with long memory, so especially when the time step is very large. But here in this example, the time step is 1. That means every time, um, so there is just one time step difference between the input and the final or the last hidden state vector. So the distance is not very long. It hasn't fully taken advantage of the long memory mechanism possessed by the LSTM. So LSTM cannot show its advantage in this scenario, or say when time step is 1, um, LSTM shows almost no advantage over the RNN layer. So what if we try to set the time step to 6 for the LSTM layer? So we can see that the train performance is around 22, and testing performance drops, I'd say dramatically. So it probably due to the factor that we talk about, that is providing more information may not improve the performance because the repeating pattern may require like 12 months information to fully capture this repeated pattern and can provide better prediction. And 6 months data will not provide sufficient information and may also just disguise the model prediction direction. Maybe when we set time to 12 or 20, something like that, maybe you may try to set even longer time step, like over 12 or 24, and you may be able to observe the advantage of LSTM. But when the time step difference is small, the LSTM shows almost no advantage over the RNN layer. Okay. Any questions regarding this notebook? All
So
good?
the quick follow-up question, Doctor. The time value, the input shape time that we pass, that determines how many recurrent blocks, if I may call it, will be there in the network, right?
Can you repeat the question?
Yeah. So that if the time that we pass, the shape of the input, that
You mean
determines
the time step?
yeah 6 or 1 or that, but we pass there. It actually determines how many the recurrent blocks in our network, right?
Yes, yes. Let me see. Can you still? Yes.
Yeah.
The time step specified in the code affect how many like repeated computation in this unrolled RNN or LSTM graph. So
Thank you,
that
Doctor.
that is corresponding to this subscript T. So if the time step is 6, then the maximum number for this T will be 6. Not 6, 5. So there will be like
The
repeated
last one
6
is
times.
prediction.
Yeah.
Thank you.
And one more thing beyond the scope of this notebook, I believe is worth noting is it's just for your information. So you may be curious, like RNN and LSTM are famous for its capability of dealing with variable length input, right? So why do we need to explicitly specify this time step 1, time step 6 in our code? So because this is just for simple demonstration purpose. If we want to build a model that can accept variable length of input, saying during the prediction time, we expect the model to accept not only just the time step 1 data and time step 6 data. We also expect it can accept like time step 12 data, time step 24 data. So we cannot set a fixed size for this input shape. Here, we need to change it to none. So after we change it to none, that means the model can accept variable length of step size instead of the fixed size we specified during the runtime, in this code. So just for your information. But after we build the model like this, we need to prepare training data that comes in variable length. So if we specify the time step number is 6 in this case, we only need to prepare training samples or training input that only comes with 6 time steps. But if we change it to none, we need to prepare training sample that comes in 1 time step, and we also need to prepare training samples of other time steps numbers like time step 2, time step 3, time step 4. We need to prepare much more number of training samples covering the variety of this time step length. Just for your information, in case you're curious about why we specify or hard code this time step number.
But
So,
is that the times input shape is none means it can be anything?
It can be accepting variable length of input data. So let's say for this model, if we specify the time step is 6, that means when you provide the data to the model for prediction, you have to prepare a data that has exactly 6 previous months data, right? You cannot provide only 5 previous 5 months data and do the prediction. That is specified by the model. That is the requirement.
Okay.
But if you set it to none, that means you can provide a data that only contain the last month's passenger number and then make the prediction. And you can, for the same model, you can also provide like 3 months data and make the prediction. You can even provide a sample with 12 months previous passenger numbers and then make the prediction. So it accepts variable length of input data if you set none in this here instead of just hard code the time step.
Okay, got it. So because you said this 6 months data is still not good enough for prediction, and so there's no solution for this.
You can try like larger numbers like 12 because 12 is more can cover the repeating patterns duration. Like it is a yearly repeated pattern, right? So if we provide enough information that can cover this entire pattern changes, it may provide sufficient information to do the prediction. Because we only provide the past 6 months information, it may just show the decreasing trend or the increasing trend and may mislead the model prediction. So although we provide more information, the extra information we provide may mislead the model prediction. That's one possibility. You can try to include more time steps
Okay.
to cover the entire repeated pattern.
Okay, got it. Thank you.
Doctor, about the variable length, I have a question on there. So, if we like do the variable length and we train up to 10 variable length, and at the inference time, if there was like something like 12, will that still adapt?
Sorry, I didn't get the question.
So,
So if we set it to none, so then
yeah, so we set to none and we do the training up to 10 slices, time steps, sorry. 10 times, so like 5, 6, up to 10. Maximum is 10 we try
yeah,
train. And at the inference time, there is a data with 12 times 10. Will that still adapt or will it adapt to like maximum up to 10?
the model can still work. The model can still work and make a prediction, but the accuracy may not be as good as the one uh may not be as good as the one that appear in your training because you train the model using the time step between like 1 to 10 and you provide longer data and the prediction cannot I think the performance will be downgraded a little bit.
Gotcha.
Yeah,
Because
but the model can still do the prediction. The downgrade is simply because it hasn't seen such kind of data before. But the mechanism of this recurrent repeated computation can accept longer longer input than your training.
Yeah, it could be due to could it be due to the fact that it's not considering 2 time steps in the example we discussed?
Not really, because during the training, what the model do is it is tuning its internal weight matrix so that the memory can accommodate all the hidden state vector can accommodate all this processed information in the like previous time steps, and it then use this memory information to do the prediction. If you involve like two more time steps, it may forget the importance of maybe the first two or few time steps, and it kind of change the information weight stored in the memory. And later on, when you do the prediction based on this memory, it will just behave a little bit different. Maybe, uh, but you need to try. I won't say it will be downgrade for sure, but you can expect some certain level of downgrade for the performance.
Makes sense. Thank you.
Also, doctor, so does that mean specifying the h time 6 time is equal to 6, that's the main parameter or variable which will upgrade or downgrade the performance? And does that mean changing epochs and batch size would influence the training, but not to that level?
Uh, Sorry, I don't get you mentioned about the epochs.
Yeah, so because how I'm understanding is the training of the model is highly impacted by how many nodes we have, which is time is equal to 6, time is equal to 1, and it is less influenced by the epochs and batch size.
For the epochs, I would suggest you observe the error curves during the training, and you need to monitor the curve to see if the curve has become like stable, and then you can stop the training. Or you observe the like discrepancy between the training curve and the validation curve to see if they just um fall apart between each other. And then after you observe the turning point, yeah, it's time to stop. Uh, do not use this preset like 100 epochs. We don't know if 100 is enough or if we need to like 200 epochs or 300 epochs. We don't know that. Maybe the model can be well trained in 10 epochs. We don't also know that. So here is just a demonstration for demonstration purpose. So we don't want to discuss uh, the training curves in very detail. So we just specify a random number here. But in your practice, you'd better observe the training curve to see if the model has been well trained or not. You do not want to publish like um under trained model or took too much time to just make minor improvements in very late stage.
Sure. Yeah. Thank you.
Excuse me, doctor. I'm not sure if I misunderstood. So you said the timestamp equals 6, then you provide six months. If you exactly 6 months data set, and this 6 months is just 6 months, does it mean? Because if you said 100 epochs, training these 6 months is just keep training these 6 months in this model?
I'm sorry, I don't get it.
Okay.
There is no direct relation between this time step and the epochs. This epochs is related to the optimization process. That would be the gradient descent or Adam optimizer, those kind of stuff. This time step is related to the model design. So there are no direct relationship between these two concepts.
Yep. Yeah, I got it that the timestamp is not no really relationship. I just get it. I may be wrong with that. You said the timestamp is equals 6. There will be provide 6 months of data set data, and then 6 months of those number passengers number features. Does it mean just 6 months, or every time you give you 100 months, then it cut into 6 months every 6 months to predict?
Okay, that's a good question. So if we set the time step to 6, we don't have this part. So if we set the time step to 6, that means there we can provide in maximum 6 input time step or 6 input vectors to the RNN. Of course, we can provide maybe 4 using the past 4 using only the past 4 months passenger numbers to the model. But what the program would do is it needs to do some padding. It needs to pad these 2 time steps with some nonsense or masked useless values. Maybe it set it to -1 because that is definitely not representing a passenger number. And you specify these 2 positions to be -1, and the program masks these uh, 2 positions, saying this 2 will not be involved in the computation, and then do the rest of work. This is more related to the implementation details. So yes, when you set time step to 6, you can provide less time step data, but you may not be able to provide more time step data, saying time step 8 or 12. So if you provide more data, you may be asked to truncate the data to match with time step 6. So you may use the latest 6 passenger numbers from the 12 passenger numbers you provided in the input.
Okay, got it. Thank you so much.
Okay, let's have 5 minutes break and let's come back at 5:15 past 8, and then we finish our second notebook. Okay, let's continue to notebook 6B. It will use LSTM to do the text generation. So it will be working on this Wonderland text file. The data inset is just some plain text. There are paragraph of text messages in the file. So first, so in this notebook, unlike the lecture session, so in lecture session we are dealing with the tokenization of the text and to split them into word by word. But in this work, we are going to split the text into characters. So instead of asking the model to generate different words, this notebook is going to build a model that is generating characters. So basically, it is using the past few characters to do the prediction of the next character. So the first thing we need to do is we need to load the data. So we specify the file name and we open this text file and read all the text lines into this raw text variable, and we convert all the character into lowercase. So why we convert them into lowercase? Because later on we need to assign unique index for each character. Convert to lowercase will reduce the number of unique index that we need to assign for the entire character site. So without converting to lowercase, we need to assign an index for example, we need to set an index for capital letter A and lowercase a, and another index for lowercase a. So we need two index for character A. But after converting to lowercase, we only need one index for each character. And then we use the set data structure of the Python. So we feed this characters into the set Python set, and the set will remove all the duplicate characters. So after create this set of raw text, what we have is all the unique characters are stored in this set. And then we convert it to a list so that we can sort the characters based on the ASCII2 encodings. So basically, we just sort these characters, sort these unique characters. And then we assign unique index for each unique character. So we use the for loop to loop through the enumerate of all the unique characters. And we are treating these characters with the index I and the character value C. And for each pair, each key value pair, the character is serving as the key and the index is serving as the associated value for this key value pair. So after we create the dict for these key value pairs, what we get is this. So we get a dictionary, and the keys are each individual unique characters. It can be the new line, space, exclamation marks. It can be numbers. It can be the alphabetic letters. So in total, and each come with a unique index. And in total, we will get 63 unique characters. These 63 unique characters will be the vocabulary. So the vocabulary number will be 63. This is the total number of unique tokens in our task. And there are in total 164,000 characters in the provided text file. Okay, then we are going to prepare the input data and the true label. And now this time it is not a regression task. It is a classification task. The purpose is asking the model to predict what is the category of the next character. So out of the 63 character class, so which class the next predicted character will fall into. So that is the classification task. And we need to prepare the training input. The training input is the previous few characters that will be fed into the data, fed into the model to do the prediction. So that will be called the sequence in. And the sequence out should be the character that we are going to predict. So here is just the code to get this prepared. So it kind of looping through the long string that is storing the entire text information and loop through this text information character by character and prepare the sequence in and the character out and store them in the corresponding data set. So the sequence in will be stored in the data X, serving as the training or testing input, and the data Y, that is the character we're going to predict, corresponding to each character sequence provided in data X. So in total, we will get 163,000 characters. So here, we are going to use the past 100 characters to predict the next character. And again, we need to reshape the data. We need to reshape the data so that we can, the format of the data is matching with the requirement of the model. And again, normalization. Here we just use the X divided by the total number of unique characters to do the normalization. So after this calculation, the input X will be in the range between 0 and 1. And we do the one-hot encoding on all the data labels. So that will be the data labels are just the character index. Okay, and then that is the shape of X after we prepare. After reshaping, so we got 163,000 samples, and each sample come with 100 characters, and each character has one associated value that will be the index for this specific character. And then we can build our LSTM model, so a sequential model, and then we use a LSTM layer that has 255 hidden units, or saying the hidden state vector should have length 256. And the input shape is x.shape1 and x.shape2. Recall that this input shape should be corresponding to the last two dimensions of the converted shape in the input data. And then we add a dropout layer to make the to provide better generalizability to the model, so and to avoid overfitting during the training. And then we add a dense layer because it is a classification task. So the number of neurons in this output layer should be corresponding to should be matching with the total number of classes in our task. The total number of classes is the vocabulary number. So that is the 63, and it is 63. So it is also corresponding to this second dimension of the Y, that is the true label data we prepared. And the activation function is softmax because we want to convert this vector of logic into a vector of probability. And then we use the cross entropy as the loss function, and then optimize the parameters using the Adam optimizer. And then we feed the model, providing the input and the associated label. And we're going to train it for 20 epochs. And this is the mini batch test for the mini batch optimization. And we can observe that the loss of this model keep decreasing while the epoch goes. So you can observe that it is still decreasing. So maybe this 20 epochs is not enough. So we just stop here just for demonstration. So we'd better just plot the training curve to see if the loss becomes stable at this point or start to converge at this epochs number, so that we can make decision if we can stop at epochs 20 or we wait for more epochs. And here we're going to test the trained model. So we just set a kind of random starting point in the entire text, and then we extract the message starting from this location, this 1468 location, and then we convert. We get a dictionary. This dictionary can map the provided character index to the character value. So it will help us to later on translate the model prediction into the string or character representation. And then we're going to generate the character. So what we are going to do is we are going to generate a continuous 1000 characters after this start location. So we just reshape the pattern to fit the requirement of the model requirement. We did the same normalization for the input, and we make the prediction. This prediction must be the probability vector because here the model, the last layer of the model is just a neuron of 63 neurons after we apply the softmax function. So it has been converted to the probability vector. So given this probability vector, we call the argmax. That means we are searching for the index for the highest probability. And the return index must be the index of the character for prediction. And then we call this into char. That is the dictionary we prepared at the beginning. So it is going to map the provided index, that is the integer, to the character representation. So now the result should be the character. And then we did the same thing for all the values that is used in this prediction as the input. So it just loops through all the characters used in the model input. So that instead of presenting a sequence of index numbers, it can present a sequence of characters. And then it write it writes the predicted character out and append the index to this one. What it do, these two rows means what we do here is kind of auto regression. So what is doing is let's think about a simple task. Let's say we use three character to predict the next one character. So maybe the entire text will be hello world. And so what it do is it is going to use the hello, these are three characters, to predict the next character that will be L. And then what it do is it append this L to the three character we used for prediction. So it will append it to the end of this list, and then it removes the first one by just extracting the second to the end of the string. So it only want to keep the last three characters. So after this line, only ELL is remained. And then in next round, it is going to use the ELL to predict the next character. Maybe it predict correctly, then it will be O. Maybe it make a wrong prediction. Maybe it predicts just a space. So it depends. So if it predict a space as the next character, the next prediction will be based on LL space and then do the prediction. So you may observe that if it make an error prediction in between, these errors can accumulate because it will make the next prediction based on the string or character list containing wrong character, already containing wrong character inside. So this kind of errors can accumulate. Okay, now we can see this kind of testing result. So we can see that we can observe like what kind of information has been learned by this relatively simple model. It can learn to generate this space between some meaningful words, although some of the word is not spelled correctly. I don't know what their meaning. And it kind of learns some words that comes in high frequency. Maybe this U and what's that need. And then there are also some words that is learned correctly, like words. There are some words that learned quite well. And there are also some like meaningless words like double H and OU. And it also learns how to use the quotation. It like tends to add some double quotation marks around the sentence. So we can observe that it learns something, but it's not perfect. Now it can still generate some nonsense character sequence. And we can this is the improved version or maybe a more complex version. So instead of using the only one LSTM layer, it is using two LSTM layer. And in the first LSTM layer, it is returning all the hidden state vectors as the output of this layer, and then add a dropout. So why we return this sequence here? Because we are adding another, just ignore this dropout layer first. So we are stacking another LSTM layer on top of this first LSTM layer. So what it do is it is treating these hidden state vectors as the input of the next LSTM layer. So this is not RNA, it's LSTM in this case. So it is treating this hidden state vector as the input, just like this x0, x1. It is treating this all this hidden state vector h as the input vector to the next layer of LSTM computing unit. Doing that. So without setting this return sequence, only the last hidden state layer will be returned. Then in that case, there will be only one on-road computation block for the next LSTM layer. That is not what we are expecting. So we want to keep this kind of on-road mechanism and sequential processing in the next LSTM layer. So we would like to set this return sequence parameter to true, so that all the hidden state vector can be returned in the previous layer. And we also add two dropout layer to make the better generalizability for the trained model. And lastly, it's the same. So we use the dense layer of 63 neurons to generate a probability map by applying the softmax function. And the loss function we will be using the cross entropy, and the optimizer is Adam. And then we train the model again with 20 epochs. I think we're using the same batch size. And then we save the weight to the disk, so that we later on we don't need to repeat this training again. And so in your in practice, so you can also try to save some intermediate weight values in this way, so that later on when you resume the optimization, you can start from this weight set instead of retraining all the parameter weights from the very beginning. And the rest will be same. It is used to generate the characters one by one, do the auto regression. Okay, that would be the explanation for this notebook 6B. Any questions? Oh, good. Okay, great. And there are, I think, two more notebooks. I will just leave it to you. So 6C will be a practice. So So 6C is a practice, but all the answer are stored in this notebook 6D, and you can take a look and to see how to work with input vector that is more than length 1. So just like what we mentioned in previously, that in the passenger example, the feature number is only 1. But here, when we are dealing with stock price prediction, we may provide more features. We may provide the open price, close price, highest and lowest value, and this would be the adjacent, the previous close price and volume. We for each time point, or time step, we have more features to provide for the input vector. So this notebook will give you a sense how to deal with this situation. And the last notebook, that would be 6E. So 6E is kind of the statistical way to do the time series forecasting. So it is also working on the passenger number prediction task, but mostly rely on the analysis of the curve statistics, like and the decomposition of the trend and repeated pattern. But in the statistical way, or say conventional way to do that, you will see that it requires a lot of knowledge and observation for the data. You need to know the data very well, or do many exploration on the data, and then to do this such kind of decomposition, like the same curve, not this one, the same curve then would be transformed or decomposed into kind of trend, seasonality, or say repeated pattern, and then residues. So it is decomposed into different component, and then do the final prediction. So it is much more complicated than our deep learning approach, and the result can be observed here. It is not as competitive as what we have achieved, even with a very naive model we just explored. Okay, so that will be the content for this lab session. Any questions? All good? And great. Then that will be all for this session. We still have the student consultation time until 9 today. And if you have any other questions, you can stay and feel free to ask. If no more questions, that will be all for today. And just a reminder, please complete the student feedback survey. That is valuable for us. Please take a few minutes to complete it. And okay, then.
Doctor, write this link to the survey.
You can find the link through the homepage of RMS. You may have received
Is
an
it possible for you
email.
to write the link if you can?
I think it's not visible on my one. So if you go to your homepage of the RMS, here. You should have a student feedback link here at
Yes.
the right
Can you
side
get the
of
link,
the
please? Can you get
homepage.
the link and paste it? Is it possible to get that link and paste it on the chat?
I'm not sure if mine is working. You may have your uh, own link for each individual, but I will just paste the homepage for the LMS, and
Okay.
you can find this link
Okay.
at the right hand side of this sidebar.
Okay.
There should be a student feedback and the link.
Thank you. And Dr. Zheng, I have a question about the exam because exam have 10 big questions and I just wondering, I answer each question like how many sentence or words do I need to write?
There's no limitation on the word. You can write as much as you can. I think it is a 3 hours exam, and based on our previous experience, the time is more than enough to answer all the questions. So don't panic about that. The time is more than enough.
Okay, thank you. Just yeah, I just worry I cannot finish all the questions if I write too many words in one question.
Yeah, but you can have a like quick scan of all the questions and to just pick up the one you are confident or easy to answer, and yeah, something like that. But
Like,
the total time
yeah.
is more way more than enough. Like previous experience, like most of students can finish in like 2 hours, like that.
Okay, thank you. So, like, for those sub questions, I use 3 sentences to answer it. It's generally enough.
Um, it depends. It depends on what kind of questions. But we will would I think most questions cannot be answered in like 1 or 2 sentences. So yeah, it will require you to do some explanations. So yeah,
I
I
see.
would
Yeah,
say
thank
read as much as you can and to demonstrate your understanding of the related topics, because if you cannot touch the key point, we cannot give them the mark. It's quite for us to give marks.
Okay, I understand that. Just I just give an example such as you want me to compare like what is the difference between L1 and L2. Then I just say L1 can make some weights 0 and make some features totally disappear, while L2 can make the square weights small and improve the generation. So they are totally just 3 sentences to answer this question. Is this good enough for you?
Um, I would also say if I were you, I can also describe what is L1 and what is L2. Like L1 is using
Ah,
like
see.
absolute values, L2 is the like squared form, something like that. And then yeah, but your answer can like secure at least half of the marks.
Okay, I get it. Thank you.
Sorry, I just have a question. The exam, it's more applicable, the rules and what you actually taught us. Is this like you just asking the simple question of the content, or you have to apply the knowledge to a problem?
Uh, it depends. Like both questions can be involved in in the final exam. There will be a few like simple like definition or explanation questions, and there are other questions ask you to like test your application knowledge of the concept. Like if you know the concept and if you can apply it in like real world scenario, or if you can analyze the problem and identify the related concept, something like that. So it will test your like different aspect of your understanding.
Thank you.
So, like you said, there would not be any much calculations, and there would not be any multiple choice questions. And we are going to have 10 questions, and each question is going to have 2 to 3 other questions. So, would it be very lengthy, and will we get enough
I won't
time?
say I won't say there is no calculation. There will be some calculation, but no equation derivation. And yes, in total there are 10 large questions, and each large question may come with 3 to 6 sub questions. It depends on which area it is going to test.
Doctor, the calculation can be done mentally without using a calculator?
Yes, they are easy calculations, so
Okay.
it can be calculated without calculators. And you can bring a blank paper for sketching, but no calculators.
Doctor, is the L1 L1 known and L2 is L2 known regulation?
Yeah. What's the question? So what are you?
I was just referring the previous student was Yan said L1 and L2. Is L1 known regularization or and am
Yeah.
I wrong with
Yeah.
this?
That student was talking about like if there is a question like explaining the difference between L1 and L2 regularization, like how to answer such question.
Yes. What I'm asking is L1 known?
L1, yes.
Okay. Okay. Thank you. One question is that is the exam question going to ask we calculate the number of the parameters? I'm quite stressed on that.
It's possible.
Do we need to write formulas in our answers?
It better demonstrate you do this calculations step by step. Like there are some benefit to show the sequence or the procedures. Like if you just give us the final numbers and then the number is wrong, you got nothing. And if you show the procedures, and you may get like part of the work, part of the marks. So I would recommend you write down all the procedures in detail.
And because there are so many formulas, look really strange. I don't think we can actually type it in the exam.
I don't think calculating the parameters will require complicated equations.
So, like if I cannot type the formula, the full formula out, I just don't type it. I just start to write the numbers straight away.
I won't. If I were you, I won't do that. I will say what parameters or which part of the parameters I'm calculating instead of just give us some just list some numbers there.
Okay.
Doctor, the Greek letters are not in the formula, no? The Greek letters.
What? Sorry?
The old formulas have Greek letters, alpha, sigma, silent, and so on. You know, all your mathematics you shown all Greek letters, sigma, they won't be there in the exam, no? We won't be able to use that them in the exam. You can use a sigma, you use sigma to sum up. We can't type sigma.
For all those answers, all the answers can be all the questions can be answered without writing equations. And if you can express the equations using plain language, or if you have a way to express it, feel free to go with that. But those questions can be answered without equations.
Okay, thank you very much.
Okay, right.
Sorry, Doctor, I come back with the L1 and L2 question. The reason I'm ask again is when I look at the because there is one of the question in the lecture PPT file, and the question asked is what is the difference between L1 and L2 regularizations? So I got the impression is that L1 and L2 is L1 norm and L2 norm, which we were very familiar with. But I did a search, Google search. It started talking about L1 is lasso and L2 is rigid regularization.
Yes, if we apply the regularization, no matter if we add the L1 regularization term to the simple linear regression, then such regression has a name called lasso regression. And if the regularization term is L2, then the regression is called ridge regression. So it's just they just come with some different name.
Okay, so in this case, that means if I answer L1 norm and L2 norm must be actually some misunderstood, and I will lost the marks. Is it if I don't understand? Means I don't understand the questions.
What questions you don't understand?
I mean, if I answer instead of answer that's the lasso and the difference between lasso and rigid regression, regularizations. That means I actually answer instead of answer the lasso, the difference between lasso and rigid regularizations, and I answer L1 norm and L2 norm, which means doesn't mean
It depends on what the question actually ask. Like if the question is presented exactly as what we saw here on the slides, you don't have to answer the lasso and ridge, because only when L1 and L2 applied to linear regression, then it is called lasso or ridge regression. But these two terms can be applied to other model, like polynomial regression. Then the model is not called lasso or ridge. So for this question, you can just explain the difference between L1 and L2 regularization. It is not compulsory to answer lasso and ridge. It depends on how the question is presented. If it is asking what's the difference between linear regression, lasso, and ridge regression, then you better know answer L1 is the linear regression. Lasso is the linear regression plus L1, and for ridge regression, you need to say that is the linear regression plus L2 regularization term. So it depends on how the question is presented.
Okay, thank you so much.
Doctor, this PDF that you are showing, is it available in LMS?
Yes, that's in week 6 updated slides.
All right, okay, thank you.
Okay. Any other questions? All good? Okay, great.
We
So,
just wanted to thank you for all of these 6 weeks and all of the long session.
that's my responsibility. It's all right. Thank you all for coming. Like keep coming for continuous 6 weeks. I know it's hard, especially for those working at daytime and you have to learn during the night session. It's very hard. I know. But thanks for keep coming for the 6 weeks. I personally enjoy like communicate with all you guys.
谢谢。
Thank you,
you
Dr.
very much.
Zen.
Thanks,
It's-
Dr.
Thank you.
It is
Thank you.
extremely enjoyable and informative.
Okay. Good luck on your final exam and the assessment tool. If you have any other questions, feel free to email me. Okay.
Thank you.
Doctor.
Thank you.
Thank you.
Thank you, Doctor.
Thank you. Have a good night.
Good night.
To
Doctor, if it is okay, can I ask